Alright, so this video is going to be on the mesh current method. And if you remember from engineering math, in a linear system with n independent variables, we need n independent equations to determine the solution. Now, we're not going to go into why this works, but we've been doing this all along. So for our very simple circuits, we're looking for one independent variable. So we write one simple equation and we get our solution. Now, as you found out in circuits, we don't always get those nice pretty circuits. So for instance, in this circuit, we have three independent variables. And if we want to solve and find all three, we might start out by writing one equation, hypothetically speaking, and keeping track of the fact that we have three unknowns. And then we write a second equation, and we still have three unknowns. And then we get stuck. So maybe we have to define a new variable, and what we end up doing is writing an extra equation, but also introducing another unknown or another variable. And we do that again, and then finally, to solve this system, to find these three variables, we end up writing 5 equations. And we think we're done, so we put it into our calculator, and well, we don't get a value. We find that this variable is still dependent, so we get a dependent equation. And if we go back to the statement that we made, the key word here is independent equations. So even though we can mindlessly go about writing our KVLs and KCL and Ohm's law equations, we might end up chasing our own tail and not actually getting to a solution. And that's where mesh current method comes into play. So mesh current method is a system or a method for creating a system of independent linear equations to solve for a planar circuit. And all this means is that for planar circuits, if we see two wires cross, we best save our time and use node voltage method just to be safe. Now, this is very good because rather than having to think about what equations we write, we're given a method, a step-by-step approach, and as long as we follow it, we can solve for all the variables and all the voltages and currents in our circuit simultaneously. So we're going to do an example. And this is our example circuit. And you notice that it is a mess. So mesh current's really going to help. So the first thing that we're going to do is we're going to highlight independent variables. Now, this is not part of the approach, but if you're going to be doing this on an exam where you're stressed, you don't want to have you don't want to miss this step because it's going to make them easier to see, and we're going to come back to these. Now, we're not going to talk about why this works, but the next thing we're going to do is we're going to label all the essential meshes. Yeah, this is really a mess. No, we're going to label all the essential meshes. So the next step is going to be label all essential meshes. Now, we actually haven't talked about what meshes are just yet, but a mesh is any path on which you can write a KVL equation, excluding the paths where we have to go across these independent variables. So for instance, following Vx, going through this 15 ohm resistor, and then going back down to Vx through this source and this resistor would not be a mesh. But going around this resistor loop is a mesh. Going around these voltage sources and these resistors would be a mesh. And this also would be a mesh if we take on maybe a larger route. But the point here is we want to label all the essential meshes. So what this means is all the fundamental, the smallest ones that you can do. So I'm going to do that now. I'm going to start over here, and we label a mesh like this. We name a current, and we draw an arrow around it. Now, for convenience, I'm going to recommend that all of your meshes go in the same direction. So if you like counterclockwise, do that. I'm going to do clockwise meshes. Okay, so I've done that. If you notice, I started with A, and I got all the way down to O. So we got quite a few meshes to do here. And something else that I should point out is that I also looked at my currents. Since we're defining currents, IA, IB, IC, we want to make sure that we're not defining anything that's already been defined. So if the currents were IA, IB, and IC, maybe we should pick our mesh currents to start at the other end of the alphabet, so we don't lose points. Another thing is, now that I'm done, I also look over it again to make sure that I haven't missed any meshes, because sometimes it's very easy to do, especially in a limited amount of time. So we actually haven't talked about what these meshes mean, but I'm going to go over it in a nutshell. This mesh here, IE, means that we just named a current which goes through this branch. So it's completely valid in every sense to say that this is IE, even down here. So what you can also assume from that information is that we can call this current here IF. And that's true, we can go all the way around the circuit doing that. But what about these currents in the middle? Let's try to find this current. And I'm going to call this IW. And we can do our KCL at this closed surface and find that IW equals IE minus IF. And we already knew that, but this goes to prove a point, because that's one way of finding the current, but we can also find that current based on the meshes on either side of that resistor. So if you notice, IE is going through clockwise, which would indicate that IE is coming in through the resistor from the right to the left. But also at the same time, IF is going through this resistor from left to right. So if we were to draw IE on this resistor, we would draw it in the same relative direction as IW. So we're going to say that IW equals IE minus IF. Minus IF because IF is going in the opposite relative direction as IW. Now, take a minute to look at that, and then we're going to do some examples. So now, the next step that we need to take, so we've already highlighted the independent variables. That's optional, but it's encouraged. We've labeled all the essential meshes. We've given them unique names. Now we're going to do KVL around every essential mesh. Now I'm going to point out that we're not going to solve for IW. That was just an example. Because now we're not going to call it IW. We're not going to introduce any new independent variables. We're going to call the current here IE minus IF. And we're going to use that naming convention when we create equations for each mesh. So let's see what that looks like. Okay, great. So now before we get started, I like to point out this little rule, which is the number of equations we're going to need, which is the number of meshes plus the number of independent variables. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 meshes. So that would be 15 plus, and it's really easy to see because I highlighted them, but 5 independent variables. We're going to have to write 20 equations to solve this circuit using mesh current method. Now, to make it really easy for the people who are grading this, we are going to explicitly state which equation we're writing. Let's see if I can frame this better. So if we're going to do KVL at mesh A, we want to do KVL here. Now we'll start, so we're going to go in this triangle. We're going to start here, and I'm going to write my KVL equation, which is going to be 6 ohms IA plus 30 volts plus 7 ohms IA plus 12 ohms. Now the current that I'm looking at going through this resistor is going to be IA minus IB. And I have to be careful about sign convention, but what happens is if I define these meshes all in the same direction, and I do the same, if I write all of my KVL equations the same, what's going to happen, and you'll notice here, is that the mesh that I'm doing, A, every current IA that's referenced here is going to be positive. And then in the case where we have a mesh which touches another mesh, it's going to be that mesh subtract minus that adjacent mesh. So here we have IA minus IB. And of course we set that equal to 0. Let's do the next one. So we don't have to write this one down. When we write a KVL equation here, we're going to write, well, we can start here, and we're going to have IB minus IA times 12 ohms equals 0. Let's do IC. IC, we can start here, and we'll have IC minus IH times 14 ohms plus IC minus ID times 11 ohms equals 0. I'm going to take a minute to write this down. So here I've written them down, and we're not going to go into detail about why this method works, but I just want to point out some things. For instance, here, what does this mesh mean? The instructions tell us to use mesh current method to write an independent set of equations to solve the circuit, and typically on the exam it'll tell you not to simplify the circuit. So here, typically we would simplify and we would say, okay, this resistor shorted, so immediately I can neglect it. And in doing so, I would just have one mesh going clockwise around this square. And this current here, well, take a look at this equation, and then that's basically what it's telling you, is that when we simplify, IA is going to equal IB. Now let's do ID. Now, when we do KVLs, remember I said that we do not want to introduce any new variables. So we could do this KVL, but we're going to get to this current source. And we don't want to have to define a new voltage across this current source for our KVL equation. So instead what we're going to do is we're going to, just like we did in node voltage method, where we take two closed surfaces on two different nodes and we put them as one. Here, we're going to do our KVL equation around both of these meshes. So we're going to neglect the branch that's between these two currents, and we're going to do KVL through this 11 ohm resistor, through this very long short, and through this 15 ohm resistor. And that's it. So that equation would be ID minus IC times 11 ohms plus IE minus IF times 15 ohms equals 0. Now wait a minute, if we have two independent variables, we need two independent equations in our system so that we get a unique solution. So here, when I indicate D, we're going to call this a super mesh, for lack of a better word, and we're going to note for the grader that we're doing it on D and E. But we still need one equation, and just by definition, we know that this current, the current, say it's going down through this 13 ohm resistor, is the current ID minus IE. And we also know that the current is 9 IY. So we're going to write this equation. And now we have two equations representing these two independent meshes. Let's do this again for F. Here I notice that IF is adjacent to II, and there's a current source between them. So I'm going to do the same thing. I'm going to make a KVL equation that goes around both of those adjacent meshes. That's going to be IF minus IE times 15 ohms plus II minus IK times 16 ohms. Are we done? No. And then II minus IH, plus II minus IH times 20 ohms. And we're done, so we set that equal to 0. And that's our equation for KVL around the IF and II meshes. But we still need one more. Hopefully you can see what that is. That's going to be 5 Siemens Vx equals IF minus II. Okay, so let's look back at our steps. We've highlighted the independent variables. We've labeled all essential meshes. We've done KVL around every essential mesh. And for the cases where there's super meshes, we did KVL around that super mesh. And I showed you how to write that extra equation. Now the next step, and this might be the last step, it might not. Depends on what you're trying to do. But the next step is going to be one equation for each independent variable. So the independent variables are the ones that we've highlighted here. Now, let's do some... Now, I want to mention first, later, so I'm not going to do... We got through II. I'm not going to do the rest of the mesh KVLs in this video. But I want to mention that when we write these KVLs, we do not want to reference these independent variables. Let me give you an example. Well, there's not a good example on here, but say that this IY was going through and this is just a good rule of thumb. It's very likely that the system you can still solve the system, but you might have some weird cases where you can't. If this IY was going through a resistor and you were doing your KVL around this loop, maybe this was a resistor as well. You're doing your KVL, you would want to still call the current, in this case, IL minus IM, instead of calling it IY. And this is just the general rule of thumb. It also works for node voltage method, but that's a topic for another video. So we're going to write one equation, back to our list, for each independent variable. And the independent variables are the ones that we've highlighted. You notice the circuit's really messy now, so it's a good thing we highlighted them when we had the chance. It's really easy to miss these if you don't use different colors, or if you're in a rush, or if it's just a complicated circuit. So I'm going to do IY. That one looks really easy. And looking at the circuit, we can tell real quick, IL minus IM equals IY. Can you see that? And then I'm going to do VY. So where did VY go? Now VY, since mesh current, we define new currents. These independent currents that were already defined are really easy to find. However, the voltages are going to be more tricky. Same thing goes in node voltage method, but in the opposite way. So to find VY, since it's a voltage, let's write a KVL equation. And the most direct path would be to go here and here, but there's a current source in the way. We don't want to define a new voltage, so what we're going to do is we're going to follow VY. Maybe we'll go through this 7 ohm resistor, then through this 11 ohm resistor, through this 13 ohm resistor, and that'll be our KVL path. So let's do that. So I'm going to start here. I'm going to go counterclockwise, so I get minus VY I'm going to get plus 7 ohms IA. And then I'm going to get plus 11 ohms IC minus ID. And we're going to go up through here. And we're going to get plus 13 ohms IE minus ID. And that completes our KVL loop. So we're going to set it equal to 0. Now in the beginning, when we were doing these meshes, it was easy. We noticed that we could say IH minus II times 20, IH minus IM times 25, IH minus IG times 21. So it's very repetitive and very easy to keep up with. But when we do strange meshes, where we have to go in a weird direction to solve for VY or write an equation for VY, it gets a lot more difficult. So be aware of that. Take your time if you need to. And take a look at these equations. Maybe pause the video, do this over again, see if you get the same things. Did I make a mistake? I hope not. If I did, let me know. And yeah. So the next step would be to write those equations for Ix, Iz, and Vx. I'm not going to do that in this video. I'll leave that up to you. And then the last step would be to put all of these equations in your calculator. Now, I recommend any calculator with an equation solver will do. I recommend the TI Nspire CAS version, the CX CAS, and we're not going to cover that in this video. But I highly recommend when you do that to name the variables the same names as your meshes. Don't call them A, B, C, D, E, for convenience. I highly recommend calling them whatever you write down here, which would be II, IA. Writing that extra letter I seems like it's going to take a lot of extra time, but it's going to save you a lot of time in the long run. Okay, so that was mesh current method. This is what we did. Remember that we always start by writing down the number of equations we need, and we check that at the end. We highlight our independent variables so that we can find them easier later. We're going to label all of our essential meshes. giving them names that do not conflict with any of the currents or voltages already labeled. And we're going to do KVL around every essential mesh, being very careful about the super meshes, and we're going to write one equation for each independent variable. So I hope this video helped introduce you to mesh current method. And to my students, if you have any questions, please email me, and or if you have problems, meet with me and we'll go over those. So thank you.